Alright, I'm going to be finding some relative extrema, which means maximums and minimums here in section 5.2, starting with number 19. Now, 19 through 25 here, they're giving us the derivative. So if you found the derivative of this thing, I got bad news for you. You need to go back real quick and realize that these are the derivatives. I already have the derivative. So what we are looking to do is I like this sign chart way of organizing the information. We're looking for places where the derivative, which is what they gave me, is equal to 0, and then what's happening with the sign of the changes as we pass those different critical points. And remember that a critical point, the definition of that is that f prime is equal to 0 or undefined. So we're also looking for places where it's undefined. Those are the things that we need to put here onto our little sign chart number line. And they tell us that we are supposed to assume that f is continuous everywhere. So even if, like number 20, this one doesn't have a denominator, so there's no undefined spots, but we're supposed to assume that all x values work on the original function. So if we find something that is undefined in the derivative, it still should go on the sign chart, right? Okay, so what do we got? Here it looks like I've got 0 and the cube root of 5. Right? Now this right here is getting squared, so when the x values pass over 0, being negative or positive, this is always positive, so I do not have to worry about how this factor right here changes the signs. It's not going to cause a sign change because this is squared right here. Any even power going to get the same thing. That is just always positive. So all I care about is the sign change here. And if I put in something bigger than the cube root of 5, like, I don't know, 5, that's way bigger, so that's definitely positive up there. And if I put in something smaller, like 1, that's going to be negative, and then there's no sign change here. So that's what that looks like. And we want to classify each one of these critical points, I've got 2 of them, as being a maximum, minimum, or neither. So here we don't have a sign change. So I have neither at x equals 0, and I have a decreasing, increasing, that's a minimum. And that's because f prime goes from negative to positive. All right, number 21. It looks like I've got a place where it's going to be 0 and a place where it's going to be undefined here, because I've got rational type of expression. All right, so in the top it looks like 2/3, and on the bottom it looks like -2. It's going to cause a problem there. So 2/3 and -2. So let's do the sign checking here. 2/3, if I plug in something bigger than 2/3, like 1, then it looks like that's going to be negative on top, positive on the bottom. If I plug in something in between these, like 0, that's going to be positive and positive. And if I plug in something like -3, that's going to be positive. This is going to be negative. Of course, taking cube root of a negative number is not a problem. Right? So it looks like I have a minimum at x equals -2, because f prime goes negative to positive, and a max at x equals 2/3, because f prime goes from positive to negative, increasing to decreasing. Isn't this fun? It's pretty easy when they give you the derivative. Less work anyway. Okay, so let's see. Here I've got the derivative as x times e to the 1 minus x squared. Now this right here, it doesn't matter what that exponent is. You can't raise e to something and get 0 or a negative number. So you could spend the rest of your days on this earth trying to do that, trying to find an x value. Can you do it? So this is always positive. So the only thing that makes any difference here at all for our sign chart of f prime, forgot to write an f prime there, is 0. And since this is always positive, when x is positive, the derivative is positive. And likewise negative. So it looks like I have a minimum at x equals 0 because f prime goes from negative to positive. And 25. How about the old natural log of 2 over 1 plus x squared? Well, let's see. Where does this cross over? So I would like to know, can the natural log of something be negative? Sure. You can't take the natural log of a negative number, but it looks like this expression in here actually can't ever be negative, so I don't have an issue with that, because this is x squared, and these are 1 plus that. That's always positive, and this is positive. So I'm interested here in what makes this equal to 0. And of course, natural log is the same as log base e. And then so that's the same as e to the 0 equals that. E to the 0 is 1. And then algebra. And then it looks like x is going to be plus or minus 1. So let's see what happens now when I try different values here. So if I plug in something that's greater than 1, like let's exaggerate that so I can get a real good sense of what's going on here. Let's plug in like 10. So when I plug in 10, I get 2 over 101. That's a number that's getting pretty close to 0. What's the natural log function doing when you're getting pretty close to 0? It's plunging down toward negative infinity. So this is negative. If I plug in a number like 0, then I get the natural log of 2. The natural log of 2, if you think about what the natural log function looks like, very helpful. It's a reason why I want to be familiar with these functions. If I plug in something bigger than 1, I'm going to get a positive number. So if I plug in 0 here, the natural log of 2 is some positive number. And then when I plug in negative whatever 10, it does the same thing that it did up here because this is an even function, right? Only thing that's happening to the x value is getting squared, so negatives and positives do the same thing. So it looks like I have negative, positive, negative. So that means I've got a minimum at x equals negative 1 and a max at x equals 1. And that's because f prime goes from negative to positive, and here f prime goes positive to negative. Great. Now, every once in a while, you might want to graph one of these things to, well, I guess here, I don't know what the original function is, so I was going to say to confirm what that looks like. But since I have the derivative here, there are some problems in the next section where I'm going to ask you just to answer all these questions by looking at the graph of the derivative. So we could do that and just talk about real quick what we're looking at and how to process that information when you're looking at the graph of a derivative. I suppose my window here looks like all the actions like around here, so maybe I just want to go from like -2 to 2, something like that. -1 to 1, I don't know, give that a shot. Oh, that's a pretty good window. Okay, so what's happening here? This is the graph of a derivative. So what information can I get from this? Well, here's a place, if you're looking for critical points, like maximums, minimums, you're looking for places where the derivative is 0 or undefined. Here's two places where it's 0, at -1 and 1. And what's going on? This is a graph of the derivative. So here it's going from negative to positive, so that must be a minimum. And here it's going from positive to negative, so that must be a maximum. And then here, we weren't asked to do this, but here, the derivative, the slope of this, the slope of the derivative, in other words, the second derivative is going from positive to negative. So this, at 0, would be an inflection point, if we were looking for that. So that's how you look at the graph of a derivative and find maximums, minimums, and inflection points. Look for the zeros, for the maximums and minimums, or possibly places where it's undefined, and the maximums and minimums of this, of the derivative, are the inflection points. All right, let's see, number 31. It's a free-for-all. Use any method to find the relative extrema of the function f. And here they're giving me the actual function f, so I'm going to have to do a little more calculus here. Find the derivative myself. I think I can handle it. This one anyway. And looking for the relative extrema, that means maximums and minimums. That's going to happen where the derivative is 0 or undefined, right? So not going to be any undefined places on this polynomial. Let's see, factor out a 4x looks like, and then I've got x squared minus 3x plus 2. That looks like the kind of thing that wants to factor. So looks like f prime's changing at 0, 1, and 2. Or at least it has the potential to change signs there. And look, none of these factors, in these factors, I don't have anything squared. So it is like, it's legit going to change sign at all of those, because these are all just linear factors. 4x, x minus 2, x minus 1. So let's see where we start out. If you plug in something negative, then you're going to get a negative, like -1 for example. You're going to get negative, 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 3 negatives. And since all of these are just to the first power, we're just going to alternate signs across there. You can, if that makes you nervous to just go through without checking the signs, you can pick numbers and try them. That's fine. You guys know the justifications here. In the interest of not making this video too long, I'm going to just say that we have here a minimum at x equals 0, and that's also a minimum, and a max at x equals 1. You know the reasons. It's the same. You think you're going to have to write those reasons when it comes to be quiz or test time? Well, yes. All right, 33, I got x cubed times x plus 1 squared. X cubed times x plus 1 squared. It's up to you whether you want to simplify this first or use the product rule. It seems like it would be easier to me because of what we're going to have to do. It seems like it'd be easier to just FOIL this out and then distribute. Okay, so now you don't have to do it this way. You could do product rule right off the bat. This appealed to my mathematical sensibilities. All right, that doesn't look like very pretty numbers for factoring purposes, but who knows? Let's see. So I'd like to know where this is 0 or undefined. It's not going to be undefined anywhere, but maybe 0. So I got x squared. It's definitely going to be 0 when x equals 0. And then I got 5x squared plus 8x plus 3. So 3, oh, sure enough, that does factor, doesn't it? So that's got to be a 5x and a 5. That's prime. So that's, if it does factor, that's got to be 5x and x. And if this does factor, of course, that has to be 3 and a 1. And if you put the 3 here and the 1 here, you get 3x plus 5x. That will do it. So I'm going to make my sign chart. Looks like I need a 0, a -1, and a -3/5. So 0, -1, and -3/5. All right, and this, so here I do have a factor that's getting squared. So I am not going to get a sign change at 0. I am going to get a sign change at these two right here. So here, this thing is an upward opening parabola, which means if I just look at the zeros of that here, this upward opening parabola must go from positive to negative to positive. If that seems a little too loose, fast and loose reasoning, you can go ahead and plug in numbers and try them. You should plug them in here. So if you wanted to plug in, for example, something less than -1, like start to the far left of your number line, you could plug in, let's say, -2. That's going to be positive, that's going to be negative, and this is going to be negative. So positive, negative, negative results in positive, and so on. You can plug things in. You just have to be careful, I guess, when you're plugging in, like picking a number between -1 and -3/5. Make sure that you actually pick something that's in between those. Like -4/5 would do it. Of course, that's always positive. This would be positive, and this would be negative. But I like to apply the math that I know from other situations. The graph of this, I know that this parabola has 2 zeros, and its leading term is positive, so it would have to look like this, which means it has to start at positive, then dip below, and then be positive again. And then I have no sign change here at 0, because that factor is squared. Right? So what do we have? I got max when it goes from positive to negative, and hold on one sec, folks. Take my phone off the hook. Coming right back. And I'm back. I think the announcements are about to start up there. That's why I ran away from you. So maximum at x equals -1, then a minimum at x equals -3/5, and a neither at x equals 0. And you know the reasons, because here f prime goes positive to negative, here it goes negative to positive, and neither here because no sign change f prime. You can't just say no sign change, right? We always have to specify what is the thing we're talking about. And you don't want to say the derivative because, you know, sometimes we're talking about second derivatives, so you're talking about the derivative of the derivative, and what if there's more than one function and all that.
Good morning, Wildcat.
Hey, Finn, could you do me a favor? Just go tap the little hang up button, or go like hang up the phone and put it back in that spot. Oh, I didn't do it right. All right, number 35. The little button where that, just pick up the phone and hang it up and then put it back where it is.
Please stand for the pledge of allegiance.
Thanks, buddy. All right, so derivative of this is going to be 2 plus 2x to the negative 1/3. Looks good, so interested in where that's 0 or undefined. This is, anytime you have a negative exponent, you have to remember that that's really like having that x on the bottom. So I am going to be undefined at x equals 0. And checking back on the original function to make sure that that is actually a point on the original function, it is. You can plug 0 in here. 0 to the 2/3 is just 0. But you can't plug 0 into the derivative. So that, you need to be careful. This is one of our critical points. You don't want to miss that. And then the other consideration is anywhere where this is equal to 0. It looks like negative 1. You can finish the algebra. I'll do it for you if you want. So negative 2 equals 2x to the negative 1/3. Negative 1 equals x to the negative 1/3. And then how do you get rid of the negative 1/3 power? You raise that to the negative 3 power, because then you would multiply those together and get 1. So I do that to both sides, so x equals negative 1. So it looks like my little sign chart is going to have 0 and negative 1. Right, that's the undefined spot. That's where it's equal to 0. And then let's try out some numbers and see what happens. So I'm negative 1/3. This is a cube root. So if I'm going to pick something less than negative 1 to test here, I'd like to pick something that's kind of like nice that I can take the cube root of. So I'm going to do negative 8. So negative 8, the cube root of that is negative 2. And the negative sign means flip it over. So it's negative 1/2. Negative 1/2 times 2 is negative 1. 2 plus negative 1 is positive 1, so that's positive. All right. In between negative 1 and 0, same deal. If I want to take the cube root of something, I want to make it something nice, so I'm going to use negative 1/8. So the cube root of negative 1/8 is negative 1/2. Flip it over, that's negative 2, times 2 is negative 4, plus 2 is still negative. And then picking something that's bigger than 0, like 1, that's fine. So 1 to the negative 1/3 is still 1, that's 2 plus 2 is 4. All right, so remember, in the absence of factors that are getting squared, we do expect to see sign changes like this. We should check, but for like regular old linear factors, things like this, even something like this, in the absence of other evidence, we should expect that we get sign changes at each of the critical points. That's the most usual thing to happen. All right, so what do we have here? I got a max at x equals negative 1. And a minimum at x equals 0. Remember that the derivative was undefined there. So that's kind of curious. So that might make me think, what does this function look like that has this undefined, where the derivative's undefined but it has a minimum there? I guess that would have to mean if the derivative's undefined but it's a legit minimum there, then it would have to be like a pointy minimum. So let's see if that is in fact the case. So I have 2x plus 3x to the 2/3. And I'll try it in that same window. That window might be okay. And there it is. There's that sharp corner. So you can see there's our maximum at x equals negative 1 right there. And our minimum at x equals 0. We could, if you wanted to, remember how to do a zoom box, zoom 1. I could make a little zoom box around there just to get a better look. I'd kind of like a better look at that, wouldn't you? Let's try that. Here it comes. Boom. So yeah, that's sharp and pointy right there. All right. So that's a minimum, but the derivative is not defined there. It is not differentiable there. And we saw that in the derivative because we ended up with a negative exponent. That puts an x on the bottom, and that's trouble. All right, 37. Where are we going to? We are going to 43. So 37, got 4 more, it looks like. Looks like I got some good old-fashioned quotient rule coming up here. X plus 3, x minus 2, so the derivative is going to be low, d high, which is just 1, minus high, d low, which is also 1. All right. And I'm looking for places where the derivative is undefined or 0. So here I have a denominator. I can't plug a 2 in here, but you should always go back and check to see, like, is that actually a point, like we did here. Here I had an undefined spot, and that 0 was still a point on the original function. That 0 could be plugged in here, but not here. So here, at positive 2, that makes the denominator equal to 0, that also makes this equal to, it also makes the original function undefined. So I don't have a point. This is undefined at x equals 2. This was defined at x equals 0, the original function. Here, undefined at x equals 2, so there's no, I can't put it here with like the critical points because there's no point there. So that's the difference between this and this. Again, if that's a little confusing, like how are these different? When you find that spot in the derivative that's undefined, you just need to check back. And you know how the quotient rule works. If your derivative is coming from the quotient rule, it's always going to be the case that something that makes this low, low undefined is going to make the original low undefined too, right? All right, so that is not a consideration for us. X equals 2 is not a critical point because it's not even a point on the function. So then that means I need to just look at the top. And the top, x minus x, those cancel out, and I get negative 2 minus 3. So that's just minus 5 over x minus 2 squared. So what makes the top equal to 0? Well, there's no x's in there, and negative 5 is pretty much never equal to 0. So there are no critical points. And if that makes you suspicious, or you want something to back that up, you could just give it a quick little graphing. Remember, critical points are maximums and minimums, or other places where the derivative is 0 or undefined. So let's just have a quick look-see. And I'm going to go back to the standard window here. So sure enough, this is where there's a vertical asymptote here. So it's decreasing. The derivative will be negative the whole time. No maximums or minimums there. And then it's decreasing again. No maximums, minimums there. So sure enough, that thing does not have any critical points. All right. Sometimes functions don't. What you going to do? Number 39, natural log 2 plus x squared. What's the derivative of that? Derivative of natural log of whatever is 1 over whatever times the derivative of what's inside. So I'm looking for things that would make this undefined. Well, that's getting squared, so it's always positive or 0 at a minimum at plus 2. So that's not ever going to be a problem. That's not ever going to be 0 on the bottom. And on the top, it looks like 0 is the only thing that's going to make that equal to 0. All right, so let's check in the derivative here. The denominator, always positive, so it just follows the sign change of the numerator, like that. All right, so let's see what we want to say about that. It looks like I have a minimum at x equals 0. But that's all there is to say. Since we're doing this, I don't want you to graph these first. I don't want you to get the idea, because I'm pulling out my calculator a few times here, that that's the right thing to do. I'm doing this afterwards, just so I can see what's happening. Is my analysis here supported by the graph of the function? Do I have, boom, minimum at x equals 0? Yep. That's a nice backup to see that. And what do we got? 2 more? I think maybe I can fit them on the same sheet. Do I have a... Oh, I got another side of this. We'll do them here. 41. I have the function e to the 2x minus e to the x. So I will take the derivative of that. I'm not going to have any denominator undefined kind of issues here. Derivative of that is 2e to the 2x minus e to the x. Don't forget that chain rule there. And let's see, where is that equal to 0? Well, what kind of factoring can I do here? I can factor out an e to the x and have to remember how exponent rules work here. E to the x times e to the x, you would add the exponents and get e to the 2x. This is a kind of factoring that comes up. It's not too unusual for us to see this, and the College Board does like to make sure that we know how to do that kind of factoring. So if you feel a little shaky about that, take a few minutes to think about what's happening there. It won't be the last of that. So when is e to the x equal to 0? Never. That's always positive. How about this? Well, let's see. 2e to the x minus 1 equals 0. So that's going to happen when e to the x equals 1/2. And taking the natural log of both sides, that means x would have to be the natural log of 1/2. Okay. So what kind of number is the natural log of 1/2 without a calculator? Can you answer that question? I really need to know, is it positive, negative, or 0, like that kind of thing. So the graph of the natural log function, I'm bringing that up in my mind, and here 1/2 would be there. So the natural log of 1/2 is definitely a negative number. Okay, so that means it's the only value I have to worry about. And also note that since 1/2 is 2 to the negative 1 power, and by exponent rules, that's the same as negative natural log 2. And boy, I tell you what, the College Board really likes to see if you know that. They like to, especially in a multiple choice context, give questions where that you get this answer, but this is the thing that shows up in the choices. So you have to recognize that that's the same. Don't believe me? Watch this. What is the natural log of 0.5? It's that. So it's a negative number, like we suspected. How about what's the negative natural log of 2? Oh boy, look at that. It's true. So, why am I doing that? I already have that there. I guess I can stash that away for 43. So, what do we do now? We just need to plug in values bigger and smaller into the derivative and see what we have. So 1, that's definitely a positive number bigger than that. If I plug in 1, I get 2e, that's clearly positive up there. And then I would suspect that this is going to be negative down here, but I better just plug in some like negative number. What would be like a nice thing to plug in here? Oh, I don't know. I mean, let's just try -1 and see what happens. So that's 2 times e to the -2. That would be, do a little scratch work over here. This is f prime of -1. It would be 2e to the -2, which is 2 over e squared, minus e to the -1, 1 over e. So what do you think about that? E is kind of like, if you need to ballpark it, it's kind of like 3-ish. So this is about 2/9 minus 1/3, and 2/9 is less than 1/3. So that is going to be negative. Another way to confirm that, you get a common denominator. That's 2 minus e over e squared, and e is bigger than 2, so that is a negative number. So as we suspected, there's a sign change there, which means I have a minimum at x equals negative natural log 2, because the derivative f prime goes from negative to positive. All right, last one, 43. I have f of x is equal to the absolute value of 3 minus x squared. Now, this is a little tricky because I do not have a way of finding the derivative of something that's inside absolute value signs. There are no rules for that. You really just have to treat it like a piecewise function. So what I'm going to do, and it's not because I'm not telling you the rules, because I think you can't handle it or something. There just aren't rules for doing that. Because absolute value signs can do different things depending on what's inside here. So let's see, what does this look like? It's a downward opening parabola with zeros at 0 and 3. And downward opening parabola, like that. That's what the inside of this is. What happens when you put absolute value signs there? Well, this piece gets flipped up, and this gets flipped up. So I'm going to go purely, instead of like trying to find the derivative of this, I'm just going to do my analysis based on this graph, because I know about parabolas and I know what absolute value signs do. So here, where is the derivative undefined? It's undefined at 0 and 3, because the absolute value signs flipped those up and made sharp pointy bits. And then it looks like, because of the symmetry of parabolas, I know it's going to happen exactly in between the zeros. That's at 3/2, 1.5. Some people call that. Here, on this side, I'm decreasing, and then I'm increasing, and then decreasing and increasing. Just have my normal change in signs there. So I've got a minimum at x equals 0, because the derivative goes from negative to positive there. And I also have a minimum at 3, and I got a maximum at x equals 3/2.